The magnetic field is an alteration of space around any moving charged particle. The magnetic field is a vector field, which means it has a magnitude and a direction at every point in space. Finally, the units of the magnetic field are teslas, which is the same as a Newton per amp meter. This is the equation for the magnetic field of a moving charged point particle. It depends upon the magnetic permeability, the net electric charge of the point particle, the distance from the point particle to the position where the magnetic field is measured, and the velocity of the point particle. The vector r points from the point particle to the position where the magnetic field is measured. The presence of the cross product in this equation indicates that the magnetic field is perpendicular to the plane spanned by the vectors v and r. We must be careful, of course, to include the sign of the electric charge in these calculations, since the magnetic fields of positively and negatively charged point particles point in opposite directions. We can also use a right-hand rule to determine the direction of the magnetic field. Point the thumb of your right hand in the direction of the particle's velocity. The fingers of your right hand curl around in the direction of the magnetic field for a positively charged particle. The magnetic field of a negatively charged particle is in the opposite direction. The magnetic field of a charged point particle forms closed circular loops around the direction of the particle's velocity. This is different from gravitational fields and electric fields that terminate or originate at the source particle. Take a moment now to practice the right-hand rule to determine the direction of the magnetic field of this particle. Since the magnetic field forms closed circular loops, it is easiest to describe the magnetic field using cylindrical coordinates. Specifically, the phi axis is convenient for magnetic fields since it too forms a closed circular loop. Now let's calculate the magnetic field of a charged point particle. The velocity of the particle will be in the positive z-axis direction. The vector r points from the particle to the position where the magnetic field is measured. Since the particle is the center of our reference frame, r is equal to rho hat plus z hat. We can determine each component of the cross product separately. This results in two different cross products of unit vectors. These cross products we can determine either using the right-hand rule or by consulting a table. We see that the resultant vector of the cross product is along the phi axis only. Substitution of this result into the original expression gives us an equation for the magnetic field of a moving charged point particle.